All right, hey guys. So today we're going to talk about GLM and shaders, and uh, this is a common topic of confusion of what is a shader and what does it do. So hopefully this will shed some light on that, and also, we'll be introducing GLM, which is a nice little library that is quite effective and helpful, in particular with interacting with shaders on OpenGL. Let's get into it. So let's start off with the GLM. The GLM is a mathematics sort of, header-only library. It's 100% templated. You don't actually have to compile it. These are headers. And what's really nice about GLM is that they try really hard to match the format of the shader side of like GLSL. And so GLM, make sure you understand, is not happening on the GPU. GLM allows you to create objects like a vector 3, a vector 4, a mat 4, all that stuff that you have in GLSL on the CPU side. And so it makes the transfer much, much more friendly. And also means you don't have to write a lot of that linear algebra stuff if you don't want to. So to get it to work, these are the most common GLM headers that you'd include, such as the GLM HPP, matrix, type, pointers, transform, the extensions, and the quaternion. Quaternion in particular being a very useful one. It doesn't use any code, any C++ code or linked libraries, and that's makes GLM very easy to integrate and use in most applications. It's really a cut and paste kind of thing. Everything's defined in a namespace, just like you would find with the STL, or SFML. The namespace of GLM is GLM. So that way you have access to all of those things without sort of polluting your namespace, so to speak. So pretty fun. Great. There's a lot of different data types that are defined by GLM, but these are probably the more common ones that you'll find yourself using. Vector 1, which is basically a float. Vector 2, 3, and 4. These are 2, 3, and 4D dimensional vectors, respectively. A matrix 3 and a matrix 4. These are square 3x3 or square 4x4 matrices. And then finally the quaternion or quat, which is used for a lot of stuff, which we'll talk about later in this course. The vector 3 is not going to only contain 3 floats. It actually has 9, but internally they work as references. So it's sort of like you can hit XYZ, or respectively RGB or PST, and these are all sort of the same values underneath the covers. It's kind of like a union, but a bit different. So internally, the mat4 is really just a bidimensional matrix of 16 floats, sorted by 4 and 4 columns, and we'll talk about that more in the matrix lecture coming up. So the job of GLSL, right, is to provide the shading language that allows you to do things on the GPU side, and GLSL has these built-in variable types, as you've seen. GLSL is not like a fully featured C++ type language. You can only do certain things there. So it's really important to note here, and I mentioned this already, the GPU does not use GLM. GLM is a CPU side that allows you to manipulate the GLSL side of things in a more direct one-to-one fashion. So it just makes code a little bit more easy to translate and understand on both sides of that divide. So what do you do with the data once the information on the graphics card once you have it? That's really what the GLSL shader is doing. Recall, this is a pipeline, and we talked a little bit about this earlier, but let's refresh on it. Right, the first stage of the pipeline is the vertex data. So you've already seen in some of the code that we've done, we've pushed vertices into the vertex shader stage. And then on the other side of the vertex shader is effectively now points that are in clip space, in that -1 to 1 sort of thing. You have a couple of optional shaders though in between that can also output vertices in clip space, such as the tessellation geometry shader, which we've talked about. And these are kind of more advanced things or specific to certain things. And then you've also got the fragment shader, which actually takes a point in a buffer and figures out what color that point should be. And so the output of the fragment shader is a color, whereas the input to the fragment shader is a point in 2D, and the output of a vertex, the vertex stage is a point in 2D, and the input to the vertex stage is a point in 3D. So that's sort of the pipeline, and the vertex shader runs at that vertex shade stage, and the fragment or pixel shader is running at that fragment stage. So GLSL, to talk a little bit about the language, it's kind of like C. It's got familiar variables like ints and floats. It's got a vector 3, it's got mat4s, and it even has flow, where you can actually combine these shaders and connect them to the other, which is pretty powerful. So, as I mentioned before multiple times, we're only going to really be working with the vertex shader and with the fragment shader. And so the vertex shader takes our positions and converts them into 2D, and then the fragment shader takes that 2D points and then converts it into an actual color. And I think that what's really important too to note here between the fragment, like how does the fragment shader know that these 3 points are a triangle or these 2 points are a line? Well, if you remember GL draw primitives and also the rasterization stage between the vertex and the fragment shader, that's exactly what's happening. So when you're telling GLSL or the GL, I want to draw a triangle or I want to draw a line, you're effectively telling that rasterization stage what to do, how to treat these 3 points as a triangle, and then interpolate between them. And the interpolation is a really important bit about how the vertex shader and the fragment shader interplay, because this point and this point, basically the rasterization layer will sort of fill in the points between the two, and the rules that dictate that come out of which primitive you're drawing. So here is the most simple, one of the simplest vertex shaders, and we're kind of gonna go through this and talk a little bit about what's going on. All this shader is doing is it's effectively taking in a position value and then passing it on, without any real changes to the next stage in the pipeline. And you'll notice that the position outputs a vector 4, and I've been talking a lot about it's 2D all the time. Well, there's a lot of reasons why you want to pass to the pixel shader the actual 4D data, but know that the fragment shader can only output a color. So even though you're passing all this data around, you can kind of imagine, well, it's technically 4D, but at this point it should be flat. So the first line of the vertex shader is this, hashtag version 330, and this is sort of a bit of a kind of metadata for the compiler, for the GLSL compiler, to let it know what version of GLSL you're using. And so this more often than not doesn't do much, but often if you use a feature that is not supported in that version that you mentioned, or you're asking to compile at a higher version than the computer that you're running on, then sometimes you'll get an error, and you can then the OpenGL application, the CPU side, can handle that error and maybe use a different shader or whatever. But for the most part, you won't find that this line with most of the things you do, unless you're doing some pretty aggressive and unique things. This will usually work fine. This next thing, so if you recall in the last lecture, we connected this line to the CPU. So this actually is connected to the CPU, which we'll see again in a little bit, by binding the attribute, the vertex attribute, from the CPU side. So this is actually where we receive data from the CPU, and then we give it a name, and then that name can be used in the rest of our shader application on the vertex. So void main is your entry point for the GLSL shader. You can have other functions in GLSL. You can define helper functions and so on. Keep in mind GLSL doesn't have like a linker, or you can't do includes, and but it is just a text file. And so if you want to get really fancy, and many people have, it's very easy to kind of create combinations and so on and reuse code. But for the most part, GLSL is not going to look at any code when you compile it other than the main, and that can refer to other stuff. But this is probably a bit of a gotcha for a lot of people. The code you write in your vertex shader is not available in the fragment shader. And the fragment shader code is not available in the vertex shader. So these are really these monolithic text files or text buffers that are passed to compile on the CPU side. So if it's not in this file, it's not there. So the main entry is where everything starts to happen. And then finally, GL position, you assign to it this value, which is vector 4 position buffer 1.0. What does that do? We'll talk about that in a second. But first, what is GL position? Because GL position isn't here, it's not on our CPU. Like, where did it come from? So the GLSL has a number of built-in variables such as GL position. You can find them here if you're interested. This link is quite good. You can kind of see there's a number of different inputs. There's a number of different outputs. Generally, you're probably more interested in the inputs, right? Like, point size, clip distance. You get to really control a lot of this stuff. And then with the fragment shader, the inputs are kind of, you already are getting that. So you can see the input, the frag chord is what you're getting from the vertex shader. But some of the built-in outputs for, there's not, yeah. So you can kind of see that sometimes these are useful, and you can kind of keep them on the top of your mind. The second thing is, what's this data here, vector 4 position buffer. So position buffer is a vector 3, and you'll see this nomenclature a lot in GLSL, where you can create a vector 4 out of a vector 3 by passing it and then comma 1. So what's happening is it's going to take the first XYZ position of position buffer and then attach to it a W of 1.0. And that's going to be passed on to the pixel shader, because the pixel shader is expecting a 4 vector thing, a four element thing. So let's move on. I'm noticing that my background's all choppy and stuff. So let me just go back to cool. I don't know if that's going to help. We'll see. Now let's move on to the fragment shader. The fragment shader, you'll notice very quickly, looks very similar to the vertex shader, but again, they're two different programs that they don't relate to one another. And so one thing, actually, you know what I can do? This is driving me crazy. Oops. Okay. It's a little bit better. Cool. Nice. Great. So let's get into the fragment shader and how it's a little bit different. And so again, you've got this version, same thing as the vertex shader. If the version is different than what you support and yada yada, it will give you an error, and this is more of a meta information for the compiler. Now this is important. So unlike the vertex shader, the fragment shader does not define its output variable. I'm not sure why this is, like why one's a built-in one. You do expect an out value from fragment. If you don't have out, that keyword out lets the fragment shader know that this is the output of the fragment shader. If you don't have that out, vector 4, you will get a compiler error. So why this is not a built-in variable, I will never know, but it's not. And it's a vector 4, keep in mind. That's important. Actually, what's the fourth value? So this is actually a color that the fragment shader is outputting. So what is the fourth color doing? Well, what is the fourth value? That's the alpha. And if you're doing any kind of transparency, alpha blending things, this is actually a very important thing. And you'll notice that 1.0 is usually the default value whenever you're outputting stuff. So this fragment is going to be equal to vector 40101. So that's RGB. So this is green, and that's a fully opaque green. If this was a half, it'd be half opaque, only if you've enabled alpha blending. So just keep that in mind until you start doing alpha blending stuff and transparency. Don't mess with this thing. And also keep in mind, and you'll notice, the return doesn't return the output. So GLSL has got its quirks. The return will exit your shader. And this is important because, you know, as you'll see later in this same lecture, GLSL does provide branching and conditionals and that kind of thing. And so you can have situations where you want to return without actually outputting anything. But if you don't set this, it's going to have some default value, so keep that in mind. So let's talk a little bit about more interesting example. And so this is slightly more complicated. And so you'll see here we've got more code. Oops. But most of the pieces are largely the same, right? We've got the version. We've got some more inputs that were not previously in our previous one. Actually, this is important. I guess I missed this. In the vector3 position buffer, this does indicate to GLSL that this is a attribute coming from the CPU. So you do need to put that in there, otherwise it won't know to connect it, that it's a connection point, and your compilation, when you try to bind the attribute on the CPU side, it will give you an error. So to kind of talk a little bit about that, the layout of this will tell GLSL what position to put this attribute. Because when you connect the attribute, when you bind the attribute, you do have to give it a location, like an ID. And this way you can sort of programmatically tell it what that is. And so the locations are kind of like bind points, almost like containers within the GLSL shader. Again, you can see here, instead of we set the GL position as we did before, but we have a new variable called color, and this is an out. And you'll see very quickly what the out is going to do. So here it's quite simple. This shader is still relatively straightforward. You take the position, you attach a 1 to it because the position is coming in as a vector3, and then you have this output vector3 color that you're just connecting. You're just taking the CPU color and you're passing it over to this output variable color, which immediately gets received by the input vector3 color. So now you'll see this fragment shader has an input, and that's coming from the CPU side. And also we've got this new thing called a uniform. The uniform vector3 solid color. What is that? So that's a special variable that gets set for every call. And this is actually where the OpenGL state machine comes into play. And you'll note that a uniform is something you can set like once a frame, or just once in a while, and it'll save it inside of the state machine, which is really a powerful thing you can do to save a lot of performance, because you can imagine the solid color being a special color, and then you connect to it. And you can see this code, the CPU side code of how you would set the uniform. You would first get the uniform location, so you pass it your program ID and your solid color. And notice that the shader program ID is the program ID, not the shader ID. And the program ID contains both the pixel and the vertex shader, meaning the uniforms are shared between the two. If you define them, you don't have to define them on both, but that's really a powerful thing where both shaders can know that information. And then you can set the uniform by providing this GL uniform 3F. There's a number of different functions of different kinds. The 3F in the GL uniform stands for the kind of data we're passing. We're passing it a vector 3, or 3 serial float values. You pass it the index and the respective variables, and so you can now imagine you're getting this information, which is pretty cool on the fragment shader side. So kind of going through this a little bit. Now we look at the output fragment. The color is going to be just the input color we received, but we have this if statement. If the solid color is not -1, -1, -1, meaning if we had set the uniform, then we're going to use the solid color instead. And then we hit return. And so this is important. The fragment color isn't output until the end of the program. And so you have all these chances to manipulate it before the end. And in this case, we have a branch. And it's like, if this is true, then do this. And this will work fine. But to point it out, right, like what if there's a for loop inside of there that does more stuff and it's out of control? Branching will give you this sort of variable rendering, which is not always something you want. You really want to be aware of it. This particular comes into play with a lot of advanced techniques like path tracing or ray marching or whatever it might be that you're trying to do. So some really, it's actually a fully fledged language. GLSL is quite powerful. And yeah, I recommend, playing around and getting this stuff to kind of feel right. And keep in mind, like, this GLSL is very similar to HLSL and even SPIR-V, and at the same time GLSL is compatible with Vulkan. So if you learn GLSL, you kind of, this is a whole kind of like class of hardware languages for like the GPU, but this language looks a lot like CUDA, right? They're all kind of the same. And so if you are familiar enough with GLSL and you can kind of get by, then you're pretty good. You're pretty on your way to understanding how machine learning stuff works and how Vulkan and other APIs work. Because this piece of the code, the shader code, tends to look pretty similar across all the different platforms. But you do have to keep in mind there are certain extensions and little gotchas here and there. But for the most part, it's the same. So, cool. Moving on to our next lecture.